So, yes, today I then want to discuss resummation, effective field theories. And the reason that we do this is because, well, there is what we call an infrared problem. In thermal field theory in general, there may be some observables which somehow by accident are not very sensitive to this, but like most observables are quite sensitive to this issue. And so the first thing to do maybe is to try to just understand this from a bit different perspectives. And for that I will write again the propagator that we had. We had a couple of representations for this scalar propagator. Okay, so now the problem is infrared means that we look at small energies. So somehow energies and much less than more or less temperature. Often it's nice to, here one sees energy compared with, not with temperature, but like 2 pi times temperature. Here it's more like energy compared with temperature, so it's if I write something here, it's a little bit ambiguous where the comparison comes from, but at the end of the day, it's sort of often nice to write it like this. Also because if one does kinetic theory, then the average energy of a relativistic particle is not T, it's like 3 times T, because there is energy associated with any direction of motion. So that's sort of a good way of think about it. And why is there a problem there? And so one can view it in different ways, and one way is, let's say, physically, is that we look at the left-hand side here and just expand it at small energies. And then the problem comes from physically from Bose enhancement. And one can say it's more or less the same physics which also leads to Bose-Einstein condensation, so that there can be many, well, in Bose-Einstein condensation there are many quanta in the ground state. In our case we don't have a chemical potential, there's no fixed particle number in this simple form, so it's not exactly Bose-Einstein condensate, but still it's the same physics, that there are lots of quanta at small energies, and that's because if I expand this guy and I assume that Ek is much less than pi times T, then I can just Taylor expand here, and the first term cancels against the -1, and then there are corrections of order which are quadratic. And so now this is the leading term, and so the leading term is then inversely proportional to the energy. And so we can make this clear by saying that if we were instead in vacuum at 0 temperature, then this propagator, maybe I call this like delta. In vacuum, this propagator in vacuum, T goes to 0, so 1 over T is very large, so this term drops out, and we have just 1 over 2 times Ek. And now, if instead we are at a finite temperature, but we look at small energies compared with the temperature, then the delta K is T over Ek squared. So T over Ek from here, and then there's the additional 1 over Ek here. And so this is clearly, since I'm in this regime, then this combination is much, much larger than in vacuum. And the higher the temperature, so to say, the more it's a problem, or the smaller the energy, the more it's a problem. So the theory at finite temperature is more sensitive to small energies because the propagator is larger. Large propagator just means that if you insert one propagator somewhere, then it gives a large contribution to this process, and so these infrared contributions are enhanced. That's the physical way to view at it. There is sort of a formal way to view at it, which is even sometimes even more useful, and that's that we look at the right-hand side. And from the right-hand side, we take first the n equals to 0 contribution, and there the omega n is just 0. And so there, immediately from the leading term, from the n equals to 0, we get exactly this, the same that we got here. It's the Matsubara 0 mode. And then there are all the other modes. So n sum t times sum. I can even, since it's even in n to minus n, I can put here 2 times t times sum from 1 to infinity. And now if I write it explicitly, then there are 2 pi t squared n squared plus ak squared. But now I see if I'm this limit that the Ek is small compared with pi times t, then this is a very small correction. I can just, at leading order in this term, I can omit this correction, then I have again the Riemann zeta. It's completely harmless. This gives some, this is not divergent. It stays finite even if I put this term to 0. So this is the leading term. And so it's of course, it's the same leading term as there, but this is very useful to observe that in this other formulation that we use, this Matsubara Samsti, the problematic mode really comes, we can isolate it. It comes just from the Matsubara 0 mode. Okay, so there's something in the infrared, and now there's a third consideration that, which then maybe it goes then a bit beyond, but let's say with diagrams, we then see why this is a problem. Why this is a problem is that, okay, let's now, like a line is a propagator, so this would be one of these propagators, and now it's inversely proportional to the second power. But now the problem is that if we then add something, we add a loop. And we had in the first lecture we had loops like this, and there's a coupling here, and I denote the coupling by g. Well, g squared in this case, when it's a quartic coupling, is g squared. And we computed this loop, we saw that it's t squared over 12. And so somehow if we consider this diagram, then there is 1 and 2 propagators. So there are more propagators, but each guy gives us then something downstairs. And then there is g squared, t squared over 12. And if the coupling is small, we would think that this is a small correction, but there is this large temperature upstairs, and it's compensated just by the dimensions by more small energies downstairs. And so at small enough energies, this term is actually larger than this term because it has more e's downstairs. And it gets even worse if one then adds more loops. Now then there would be even like Ek sixth and then g squared over 12 squared from the 2 loops. And so one sees that it gets worse and worse if we add loops. And so that's a breakdown of the perturbative series. And so then we have to do something. And that's adding all these terms together is then resummation. In this particular case, it should be kind of fairly obvious what to do. This is like a mass correction. And so we should just add this thermal mass to the propagator. And then we should recompute our diagrams with this thermal mass added. And then things should be just fine. That's kind of the simplest case, but that is then the resummation. And in a general situation, the problem is that it's not always just a simple correction to the mass. Often it's something more complicated. Okay, so now then some effective theories. So now when we when we isolate the problem, then we want to cure it. And of course, then the first thing you might do is we just draw diagrams. And if we manage to isolate the diagrams which are kind of problematic, then we may just take those diagrams and sum them, and then we may be happy. But this is a little bit tedious, because you have to be very careful to identify all the diagrams, all the correct diagrams. There are so many diagrams. How am I sure that I identified all the diagrams? So it's much more convenient if one manages to find some kind of an organization principle for where the problems are and how one can handle this. And so usually when we have a situation like this, that we have some problem somewhere, then what we try to do is we try to construct an effective theory for the problematic modes. And then the other modes are unproblematic, and we say that we integrate them out. And then we look at this effective theory, which only contains the problems. But the trick is that while we kind of postpone the problem, let's say we like the effective theory for the problematic modes, let's postpone the problem and first do the easy part by integrating out the easy modes. Then while doing this easy part, then sometimes it happens that we also cure the problem, that our effective theory is then less sensitive to the infrared than the original theory. And that's kind of the magic of these effective theories, that just by constructing them we may already have done something good. Okay, so now there are many different effective theories, and we don't have time to discuss everything, but let me draw kind of a diagram where now we imagine some observable, which now in general is a function then of energy, of frequency. I often use omega for energy, but it's frequency, and then spatial momentum k here. And then I put here like a light cone diagonal. Here is a light cone. So maybe the first at first one might think that okay, physics is just by causality. Physics is usually inside the light cone. But when we are doing statistical physics, that's not the case. Things can be correlated also in the space-like domain, because they feel the same thermal. They may have a common cause, so they are part of the thermal medium. If there's a fluctuation in temperature somewhere, there can be also a fluctuation in temperature somewhere else. And indeed, we correlate things at the same time, as we already did before. Correlating things at the same time means that in this diagram, it effectively means that we are doing physics which is then independent of time, because if we do something same time, means that also that the time as in total doesn't really play a role, and that in frequency space that really corresponds to having omega independent things. Okay, so now in this diagram then there are different effective theories, and we'll discuss a few of them, but so what now plays an important role here is a scale then, and let me put the scale like here. And that is the scale that one, if we look at here where the problems are, we see that the problems are worse and worse if we make the energy smaller and smaller. And however, the largest value of energy where we get a problem is when each addition of this upstairs thermal mass compensates for what is downstairs. So what I'm trying to say is that there's a problem if Ek is less than or equal to G times T. If that's the case, then while adding something, it's not small, it's large, it becomes larger and larger. So G times T is then the scale that plays a role. And G is, for me, so G is a coupling, it's a gauge coupling, and I would assume that G, often one writes G is less than 1, but actually if we have this convention, it's nicer to write G is less than pi, and that's also nice because if one actually does some computation, whenever you get G's from vertices and you do some loop, you also get 1 over pi, so this is a more natural combination to compare. So, okay, so with this rule, all the couplings in the standard model, even the QCD coupling, is small when we are at high enough temperature, let's say GeV and above. And so then we have here some scale, and then the pi t scale somewhere, the hard scale is somewhere here. And so now one of the effective theories we will discuss is then sort of a kind of a broad theory valid in all of this domain of soft momenta, soft energies, and that we will call the HTL theory, hard thermal loop theory. And that we will discuss today a bit. Okay, then there's another effective theory which I will also touch briefly because I think it will probably play a big role in the lectures on phase transitions then in the next weeks. And that's a theory which is, at first sight, it might look less powerful because it is its domain of validity is restricted. It's not, you cannot compute everything with it. Basically, you can only compute things which don't have real time, or at least at first sight, that's what it looks like. So it's an effective theory which is valid somehow here on this axis, just looking at space-like physics. And that we call DR, and that stands for dimensional reduction, dimensionally reduced effective theory, and I'll introduce that in a second. So less applicable, narrower range of applicability, but the benefit is that actually this theory somehow is better understood than the HTL. So better understood by that I mean it has a simpler structure, and we can also basically we can go to any order. Sort of we are understanding what's happening to all orders in perturbation theory. Let's say maybe to some extent even beyond perturbation theory. There's no restriction of what we can do. The HTL is broader construction, but it's not so clear if we wanted to do a more and more precise computation. It's not so clear how to do it, because usually in effective theories, if you want to be more and more precise, you have to start adding operators, like higher dimensional operators. And in the DR, you can do that to any order. In the HTL, the structure of the operators is much more complicated, and it's not so clear how to classify all the operators, for instance. Now, there's one remarkable thing about this dimensionally reduced theory, and that I want to indicate today. So, like when it was conceived, and for most of the applications, one really thought that one has to look at these static quantities. But maybe 15 years ago or so, there was a really important paper where somebody realized that actually there's kind of a magic that if one looks at things which are very much non-static, so really light-like physics, and technically light-like a little bit below the light cone, so still space-like, but actually light-like, approaching the light cone from here. then there's a mapping from this physics to the DR physics. And ultimately why this works is then kind of really required some deep insight about causality, for instance. That even though there are non-trivial things here, then still it is a space-like domain. And if you move some curves here in the space-like domain, then you shouldn't meet any kind of serious singularities, because there's just no causal physics taking place here. Whereas in the time-like domain, there can be anything. There can be all kinds of physical phenomena here in the time-like domain. Okay, so this I'll indicate that a little bit. So these are the main things I want to discuss, but then there are also other constructions. So one thing which is in some cases quite useful is if you are looking at, again, if you are close to light cone, but you are looking at then very hard, large energies, large momenta somehow in this domain here. Then there's another effective theory which is called LPM, Landau, Pomeranchuk, Migdal. That's something that one attacking some practical problem in cosmology. Sooner or later one might be confronted with this concept. But it's again, it's quite a bit, it's a bit more complicated. And then there are also some other constructions. For instance, there's a very interesting construction here at very, very soft momenta here, which is called, it's sort of, I want to mention it because it's a bit related to what we were discussing in the first lecture, namely it's some kind of a Langevin equation, but now it's non-abelian Langevin. Yeah, but it's a narrow domain of validity, and so it's not so often that one needs it, but if one ever needs it, it's quite a nice thing to learn. Okay, so today the goal is to discuss, I first discuss a bit the dimensional reduction, and then in particular the HDL. So dr, dimensional reduction, and so, the idea is simply that we write down effective theory for those modes which look like the problem for the omega n to 0 modes. Okay, why do we call it dimensional reduction? Well, if we think about it not in frequency space but in configuration space, then the reason that we had these discrete frequencies was that we had realized that when we do something like evaluate the partition function and write down the path integral, then formally we are on this circle where the time direction becomes compact and has the periodicity 1 over t. And so now if one then makes so often we say that now if we somehow make temperature large, then the radius, the diameter of this time-like direction, it just shrinks, and so then we are left only with the spatial coordinates. And so in this case, in this sense, it's a dimensional reduction from 3 + 1 dimensions to 3 dimensions. So it's so in other words, mathematically it's exactly the same as as Kaluza-Klein reduction, but Kaluza-Klein is if you have some compact direction in the space-time, in a space direction, and then you make that space direction very short, then you get the reduction. So here it's really in the time direction. Okay, so now I want to kind of directly go into gauge fields. That turns out to be interesting. And so gauge fields, gauge fields means that we have gauge symmetry. So gauge symmetry means that I have gauge field mu, and my mu is now I write it as a matrix. These are generators of a gauge group, and then some matrices, and these are the real components. And there's a gauge symmetry. That means if I make a gauge transformation, if I transform this gauge field, I can write U dagger, then the action should be invariant. Okay, so now this becomes interesting because if we look at the zero modes, these Matsubara zero modes, then this means that if we look at them in time, in my imaginary time tau, then if my Matsubara mode is 0, then this means that this field just doesn't, this 0, the exponential is 1. So this field doesn't depend on tau. That's just the physics here. I mean, we have shrunk this dimension to 0, and the fields depend on the spatial directions, but not on the time direction, if the time direction is very small. So everything, our degrees of freedom are tau independent. And so if we look at gauge fields, this means that there will be a distinction between the spatial components of the gauge fields. If I do a gauge transformation in the spatial components, my I is a spatial index, then it's still a gauge transformation. Okay, maybe I is not good because there is, let's say, k. Not to confuse with the imaginary unit I here, U dk, U dagger. That's a gauge transformation as this one. But if I do a gauge transformation in the time component of the gauge field, then the first term is like before, but in the second term I would have a time derivative here. But if I have restricted to fields which do not depend on time, then I should also consider gauge transformation which do not depend on time. It doesn't make sense that I first restrict to fields which don't depend on time, and then I do a gauge transformation which takes me out of that set. So if I remain within the set of the fields that I have chosen for the effective theory, then I should also consider gauge transformations which are time independent. But then for mu equals to 0, this term drops out. So this term is not there. And this is a gauge transformation, but this is not a gauge transformation of a gauge field. This is a gauge transformation of a scalar field. More precisely, this is a scalar in the adjoint representation. So somehow, by this compactification, the gauge, the previous gauge fields, in some sense, the set of gauge functions that we are now considering is smaller, and therefore one gauge field component is no longer a gauge field, but becomes a scalar field. But that has an important implication, because gauge symmetry is a strong symmetry. It protects the fields from, it gives them properties. It protects, it guarantees renormalizability, for instance, famously, but it also protects them from getting terms which are not gauge invariant. But now the A0 is no longer a gauge field, it's a scalar field, and therefore it is less protected. And so in particular, if we now then write an effective action for these modes, then it looks as follows. So effective action is an integral over the volume. And then normally we would have an integral over time. But now, since nothing depends on time anymore, then we just get 1 over t. 1 over t is a remnant of the integral over time, 0 to beta, 0 to 1 over t d tau. Since our fields do not depend on time, since they are Matsubara zero modes, we just can carry out this integral and it gives us 1 over t. Just like in classical statistical physics, so it's not so, in this sense, it's kind of even like nice that there is 1 over t. It looks like what we have learned in statistical physics, but here it really comes from the fact that there's no dependence on tau. And then there is, okay, and then there's the action. So now for lack of time, I will sometimes one gets a bit confused about signs and so forth, but for instance, usually when we write down the action for gauge wheels, in Minkowskian we have a minus 1/4, and so now I don't want to explain why you can use it as a convention that I will not write any minus sign here, it's just a plus, but that, let's say that's an overall convention. But to remind us ourselves of that overall convention, also when we are imaginary time, when you're Euclidean, usually we then set all indices down. I mean, in Minkowskian, there's always one index up, one index down, as a reminder of the Minkowski metric, but in Euclidean, we put all indices down. So I write now all indices down, and then I write here Fij, Fij. And so that's the usual kinetic term, now with the plus sign, but now only with the spatial indices, because the spatial gauge fields are still gauge fields. I don't have 0I, because the 0 component of the gauge field is not a gauge field. Instead, I can add here a kinetic term for a scalar. And it's an adjoint scalar, so it's a covariant derivative in the adjoint representation. Okay, again with a plus sign, but let's not worry about that. So that's a kinetic term. It still has a gauge charge. That's why there's a covariant derivative. It feels the gauge interaction, the spatial gauge interaction, but it is not part of the F because it's not a gauge field in itself, just a scalar. But now we can also write many other terms. So for instance, we can write 1/2 A0 A0 A, and then a coefficient here. This we call d by mass squared, and the d by mass squared is precisely the type of a mass which we saw today in the diagrams and which we computed in the first lecture, namely it is proportional to g squared from the vertices, and then it is proportional to t squared. And so that's now these are the modes which we have integrated out when we construct this effective theory. And then there are some coefficients which we don't need to No. And so why is this term there? Because, well, it's there because A0, A0, A is the same as trace A0, A0 as matrices, or more precisely 1/2 A0, A is a trace A0, A0. And if we now make this gauge transformation, then there will be U dagger and another A0 U dagger, and the U and U dagger they give 1, and then there's a U dagger on the right, U on the left, but because there's a trace I can put it on the other side, and they just compensate, cancel, and so this term is gauge invariant now in this set of gauge transformations, and therefore that's why it should be there, it should be allowed. We have to put it there. We don't know a priori if the coefficient is non-zero or 0 or non-zero, but then once we realize that this term might be there, then we just put it there, and then afterwards we compute the coefficient, and then we find that indeed it's non-zero. And then there are of course many other terms one can add. Couplings, and so forth. In an effective theory there are always effective theories are not renormalizable, so one has to allow for all kinds of terms, many terms, infinitely many terms. And the whole key of the, well, of course the key of the, at the end of the day, if we want to be precise, if we want to analyze how good is this construction, then we have to show, we have to analyze what is the contribution that these higher dimensional operators give. And when I said that the DR theory is a very good effective theory, that means, what it really means is not only that we have computed these coefficients to some order in perturbation theory, but even more importantly, conceptually, is that people have analyzed how important these operators are, and people have showed that these operators indeed give a suppressed contribution to physical observables. And therefore it makes sense to truncate. If you want a certain precision, then the precision tells you how far you have to go. And for most quantities in cosmology where we don't need 1 per mil accuracy or so, then we can well live with this kind of a thing. And then if we wanted to do a really precise computation, at some point we would have to go down, but we can do this. We can compute the operators, we can analyze how much they contribute, and this could be done. For some of the other effective theories like the HDL even, it's not so easy to, it's very difficult to say how important the higher dimensional operators are if you cannot classify them, if you don't understand their structure. And so that is then a challenge if you don't know that. Okay, good. So that's the dimensionally reduced theory. And now one could say a lot more about that, and I think there will be a lot more about that in the lectures on the phase transitions. So today I wouldn't like to spend much more time on that. Maybe are there immediate questions on that?
I always have a very, well, maybe naive question. That is, say this field is, for example, the photon field.
Yeah.
And this zero mode gets thermal mass.
Yes.
Then in the high temperature, in a high temperature regime in the early universe, would these somehow change the relativistic degrees of freedom in the plasma?
In a sense, yes, but it depends on because okay, let me. Well, when we, yes. So yes and no, because really this, how should I put it? So the important thing is that what I had this diagram somewhere about so there are new effects at small frequencies, small momenta. But then when we compute something which we normally associate with the relativist degrees of freedom, for instance, the pressure or the energy density. Then the leading order and even the next to leading order, they don't come from this domain. They come from hard momenta, I times t. That this kind of hard momenta are what give us the Stefan Boltzmann law or so. So therefore, when we usually count the number of degrees of freedom just to estimate what's the energy density or so, then we don't need to worry about this. It's only if we are doing physics where it's really important to know the equation of state, not only the t to the fourth, but corrections to it. And then at some point you have to start worrying about that. And then indeed there is effectively you can say that, but in that situation then just the number of degrees of freedom is anyways not a good concept, because the important thing is then the interactions. And so this is really, they modify the interactions more than, However, it's then a bit, it gets, so to say, more interesting if you are looking at something more differential, so some kind of like scatterings or so, because in that case it can be that these masses play a role even at leading order, because if something which you thought was massless now gets a mass, it can open up a new channel, for instance. And so that's very important already at leading order. So in that case, it's really, really very important, even for photons. And that's not only for cosmology, even for astrophysics, there are some, like cooling of neutron stars, there are some processes where we think that effectively the photons get a mass because of some interactions, and then that opens up a new channel of how some effective photon can decay into neutrino-antineutrino pair or something, which wouldn't happen in vacuum. So, yeah. Okay, anything else? Yes?
So what we've done here is that we used a gauge field, we compactified along the time direction, and then claimed that for the new coefficients that we get for the A0 mode, which behaves like a scalar, that in those coefficients we're putting in all the, the IR issues, right?
In that coefficient are the ultraviolet issues. In that coefficient are the issues that we integrate out the other modes.
Sure.
But we haven't yet, then okay, so and the fact that this guy becomes massive now, that kind of cures some of the infrared problem, because now it has this mass, so my propagator has a mass, and that screens the most infrared thing for this particular field. We may still have a problem with the other gauge field components, and this we haven't cured yet. And for that we would have to analyze this theory and see if there are other problems there. I kind of only cured, by constructing this theory, I see that I have resummed the problem for a particular polarization state for this one, but not necessarily, and in fact not for the other ones. And they would, yes, they are still there.
Okay, so what was the motivation behind choosing a gauge theory, as opposed to just defining like a scalar field theory with like a thermal mass?
We could also look at the scalar theory. We look at the gauge theory because, first of all, there are gauge fields in nature. Second, because we will go now to the HDL, and there I want to make a connection to the HDL is very interesting for gauge fields. So that was the question.
Yes, sir. Many more basic questions to understand this equation. So you compactify on temperature, and how you add temperature. So basically, we're understanding you have zero modes living on the surface, and we're analyzing the zero modes. How I add temperature on these zero modes? Like, can I compactify on different T? Like, what is happening? And the daylight mass you add because you have this freedom of adding it, but it doesn't come from the compactification. Right?
It comes from the integrating out the other modes. So first I can add it, just from the symmetries, I can add it there, but I don't know its value. And then I determine its value by, as we say, matching it to the full theory, or more physically by integrating out the non-zero modes. And thereby I find then what this actually is. I can show that it's non-zero, I can find its actual expression. So that's where this comes from. Now, now if you ask then how do these fields feel the temperature? Well, one thing is that there is still this overall factor here. And that, for instance, that is really like classical statistical physics. In classical statistical physics, there is a temperature. If you compute the Hamiltonian, so to say, corresponding to the system, there is a temperature there. So it is still a thermal system, but in the sense of classical statistical physics, which we didn't impose. It really comes from this construction. So it's kind of a... Some people like to say that when we do this, we go over from quantum statistical physics to classical statistical physics. But for us, it's just an effective field theory. Okay, then let's go on, and so now we come to the HDL. So HDL stands for hard thermal loops, it's called. And as it's often the case, this is not really it's not really a good name, because what we do is we construct an effective theory. Now I want to do it again. I want to do it for gauge fields because it's even more interesting than for scalar fields. And so then we are integrating out something. And our effective degrees of freedom are these soft modes. GT scale physics. And what the hard thermal loops are, these are the degrees of freedom which we integrate out. Just like we integrate them out to get the ME squared, then also here in the construction, we imagine that we are integrating out hard momenta. Pi times t. And by doing this, we modify the properties of the soft modes. But the effective theory is the effective theory for the soft modes, not for the hard modes. We have integrated out the hard modes. So it's a bit silly to call it the hard thermal loop theory because there are no hard thermal loops left. We have integrated them out. It's really an effective theory for the soft modes. But anyway, this is now how we call it. Okay, so what's the difference compared with the DR dimensionally reduced theory? The difference is that now we really want to we want to keep access to dynamical phenomena, whether inside or outside of the light cone. So want to keep access to omega non-equal to 0. And now if we do the construction, we can still do the construction in the same imaginary time formalism with which we did the dimensionally reduced theory. But if we do it like that, then this means that at the end of the day, we have to do an analytic continuation. This is this weak rotation in frequency space that we already saw yesterday. But mathematically, you cannot do an analytic continuation. You have to know the analytic dependence of your function on the omega n. If you just know the value of some function at omega at the discrete set of omega n's, it's not enough. You have to know the full functional dependence. Otherwise, you cannot analytically continue. So need full dependence. And so that's why it's more complicated. We cannot get rid of the time direction. We cannot get rid of the omega n's. We have to keep them there. Okay, so Okay, so now I want to kind of write down then the action or a part of the action. Okay, maybe it's not so important, but usually I often have, maybe sometimes it's good just to clarify my notation. So often, notation. I often have a notation where when I denote something by k, which, okay, if I denote something by like a capital K, then it would be omega n k. And then sometimes I try to write something like nice k, then that would be like after the analytic continuation. But whatever, boring k or fancy k, it's kind of for some observable, like let's say a probe, external probe, like the form momentum of some particle that we are producing, so external. And then if I instead write a p, then for p I would write the Matsubara modes then with the Pn. I think yesterday we also had it like that. And then a nice p would be P0, P. And that would be often like then what's in the loops, so to say, internal. Okay, that's just, it's kind of how I myself like to keep them distinct, just that it doesn't get confusing. Okay, so now what I want to do is I want to write down then the effective action for the hard thermal loops, or rather a part of it, to discuss a part of it. And I'll discuss a part of it, and we'll take just a quadratic part. So part of the effective action. And I write this now directly in momentum space. So I put here this sum integral that we saw. And then I put here a mu minus p, a mu p. And now if we take the normal tree-level Lagrangian, then what comes out here is p squared delta mu nu minus p mu p nu. Again, I'm Euclidean, I'm imaginary type, therefore all my indices are down, as a reminder of that. So that would be sort of tree level. But now when we construct the effective theory, then we are integrating out these hard modes, and they correct the structures. Just like in the dr, they gave us this me squared, the d by mass squared, then in this case they give us something. But now we have four momenta here, and so what they give us is more complicated. And I denote it by p pi mu nu p. And so now of course it's kind of an age-old discussion. If you compute some, even in QED, if we compute some corrections to the photon polarization, we talk about the photon vacuum polarization. Here it's like a medium polarization, now not of the photon, of a non-abelian field, but still it's a correction, it's a polarization. Then there is one property that we know that these corrections should satisfy. Of course, if we do a practical computation, we can verify it, but quite generally we know that they should satisfy like a word identity. And the word identity would be that it's transverse, that this correction is transverse. Just like this part is transverse, then also the correction should be transverse. Okay, so if we were in vacuum, then there are not many structures which one can write down which satisfy this. And so if we are in vacuum, and also if we didn't have, let's say, suppose that we don't have any, suppose that the theory is such that there is no breaking of discrete symmetries like parity and so forth, then the only objects by which I could construct such a tensor are either the Kronecker delta or then the form momentum itself. And so then we would know that this structure has to be proportional to the same transverse projector which we have there at the tree level, and then times some scalar function phi p squared. But now in medium, it's no longer the case because we break Lorentz symmetry. So medium means that there is a special frame, and the special frame is the rest frame of the medium. And so normally, and also I will be doing it here, we work in the rest frame of the medium. So there is a special frame. So if one wanted to work in a general frame, one could introduce this 4 velocity of the medium that we had, but it's much easier, it's complicated enough to work in the rest frame of that medium. And now what that implies is that we have more structures. There's no reason for us to be democratic in the indices, in the space-like and time-like indices. And this means in particular that I can introduce, I will introduce now another projector. And I'll denote this by P, projector, and I denote it by T, so it's somehow transverse, but transverse, of course this is transverse, but this transverse means transverse, well, we'll see in a moment. I denote this, well, this one will only be non-trivial for these spatial indices. U is spatial, nu is spatial, and then transfers into spatial. Where small p is the absolute value of the spatial momentum. So this is transverse. This is transverse with respect to the form momentum. Because if I project with a 4 momentum, then the 0 component doesn't give anything. I have a projection with a 3 momentum, but this is transverse with respect to 3 momentum. So therefore, it's also transverse with respect to 4 momentum. And normally in vacuum, we wouldn't do this because it makes a distinction between the spatial indices and the time index. But now we are allowed to do it because we are in a special frame in the rest frame. Okay. And then I will introduce another one. So now we have something new, and then I introduce what we call E, and this E is well, as we will see in a moment, it's basically the same E as we had in the d by mass squared. This refers to transverse with respect to spatial momentum, and this E is somehow electric. It refers to electric. The d by mass we also call the electric mass. Physically, it means, in QED, it means that the electric fields get screened in a medium, so it's electric. And so this is, what is this? This is if we take what we would expect from vacuum, we take that and then we subtract this other one. And now it's fairly straightforward to see that these two projectors they are transfers and they are both projectors. If you do project twice, you don't get anything new. And so these are then two projectors. And so this means that, again, just out of symmetries, this means that I would expect, if I computed this, I would expect that in general it can have a projection on both parts. So there can be something which has this transverse projector and then some scalar function, and I denote this by then a transverse pi function of p, and then there can be another part which is proportional to the electric, and again a scalar function p pi e of p. And this is just like let's say at this moment it's just like a conjecture that this could happen. And then again, to see if it really happens, we would have to do a computation. We compute this diagram. Well, not only this diagram, also all the other diagrams. Of course, we have to compute also this diagram, also gauge field. We have to do some gauge fixing. We would have to put some ghost loop there. And then we may include fermions, and we may include scalar fields and everything, so we have to compute all of them. And then we get functions. And obviously this computation we are not going to do today, but it can be done. And what I want to show you is that these functions are very interesting and non-trivial. So in particular this one I think I can remember, and it is proportional to exactly the same d by mass as we had before, but then now it's momentum dependent, so it has 1 plus pn squared over p squared, 1 minus I pn 2p, and then most importantly a log here, IPN plus p, IPN minus p. Okay, so now let's discuss this a bit. And first thing we may check is that what happens if we take if we put Pn to 0. If we put Pn to 0, then this scalar function becomes, if Pn is 0, then this term drops out, and this term drops out, and we just have the me squared. But we should also think about what happens with the projectors. If we put Pn to 0, then Pe, if we take both indices spatial, then we get delta ij minus p, and now spatial indices, so pi pj, capital P squared, but because Pn is 0, then the capital P squared is the small p squared minus Pt ij, but Pt ij is exactly this one. So Pa ij is 0, Pe 0i. If I have one time like one spatial index, then delta is 0. The first term is also 0 because there's one Pn, and Pt is anyway 0 because it only has spatial indices. That's 0. And if I take PE 0, 0, then I get 1 minus, then I get Pn, now 0, 0 here, but 0, 0 is Pn is the frequency squared, but the frequency was 0, so that is 0, and Pt is 0 because it only has spatial indices, so it is 1. And so now we see that in this limit, therefore, out of that part, out of PE u nu by EP, Pn goes to 0, it is just delta mu 0, delta mu 0, me squared. And that's precisely what we had in the dimensionally reduced theory. So that's good. So we go over into the dimensionally reduced theory if we go to this special limit. But now we have a more general description. Good. So now now I want to discuss what it implies that we have this momentum dependence here. So, okay, so normally now let's look at the propagator. But now we look at the propagator. But now we look at the propagator in this effective theory. So we have first constructed this theory, and then we would like to use this theory to compute something. So then we construct the propagator within that theory. So we look at the propagator within the HTL theory. And since now our action was corrected by these self-energies, then also the propagators will be corrected. And so then a general propagator will look like this. It has that one can decompose it in terms of the same projectors, and then there will be p squared and then the scalar function in that channel. And then in addition, there is, of course, to construct a propagator, you have to, this is an inverse of the quadratic part of the action. So to be able to construct the inverse, one has to do gauge fixing, one has to make it invertible, so there is then some gauge parameter, as usual. These are in the transverse part, and this is then the longitudinal part. And so now then what we define is then we define a spectral function. And we define spectral functions separately for these channels. So, for instance, for the electric, but we define them separately for T and E. They are of the same type as we've seen. They are imaginary parts of then these structures that we have there. Let's to make it simpler. I'll pick up one like the E. Imaginary part after the analytic continuation that we have seen many times. Okay, so now usually when we do field theory and Feynman diagrams, I mean, we have this kind of thing. We have 1 over p squared, but then there is a mass term here, mass squared. If we, in that case, if we did this, we put there a small I epsilon, I0, like in the Feynman description. This is not exactly the Feynman description. This gives us not a time ordered, but a retarded, but that doesn't matter. There's a small I epsilon, and then we take the imaginary part. Then, if this were constant, then what comes out of this are just Dirac deltas. I mean, if you have something delta plus minus I0 plus, then this is the principal value, and minus plus I pi Dirac delta. And if we take the imaginary part, then the principal value drops out, and we get Dirac deltas. And Dirac deltas are the reason, if we take this imaginary part, are the reason why particles are on shell. This constraint is a constraint. It says that the energy is given by the momentum and the mass. It puts things on shell. That's the usual story. That's why particles are on shell. But now we have momentum dependence here. And that completely changes the story. It's not constant. And not only is it not constant, it has a non-trivial structure in the complex plane. And that comes from this log, because we had in this guy we had this kind of a log. And now if I do analytic continuation, so Pn goes to minus I, so that means IPn goes to P0 plus E0 plus, then I get the log of P0 plus P plus I0 plus divided by P0 minus P plus I0 plus. And a log has cuts. And so if we look at complex plane of P0, okay, let's imagine first that the P0 and P would be real. So we walk along the real axis here. I put here minus P, I put here plus P. If my P0 is larger than plus P, then this is positive, and this is also positive. Both are positive, then there is a small imaginary part, but if both are positive, it doesn't do anything. So everything is fine. Here, everything is fine. But if I go in this domain, then P0 is less than P. So this is all of a sudden negative. This is still positive. But now I have a log of minus something here. And that's ambiguous. Well, I have I0 plus, so this tells me on which side of the cut I am. But I have to be very careful. So basically I have log of minus 1, and log of minus 1 is like minus I times pi, plus minus I times pi, depending on from which side I go. And that's not a small number, it's a large number. It's a number of order unity. So here I have a cut. I have a cut here. And so that then that then is not, it is, it so happens that this cut is not, it's not just some mathematical mathematical complication or so. It's extremely important physics associated with this cut. And this physics, there's nothing, this physics is not, I wrote this for non-abelian fields because usually in particle physics they are maybe even more interesting than abelian ones, but one can also write the hard thermal loop action for QED. In fact, it was first done for QED. And these same functions appear in QED. Then it's not proportional to the non-abelian coupling, it's proportional to just the electromagnetic coupling. And this cut is there, and the physics that is associated with this cut goes under the name of Landau damping. So obviously it's known physics from QED already. And damping, why damping? Damping because there was this imaginary part. Imaginary parts have always to do something with damping. But this is a special type of damping because it's only in this domain that P0 is less than P. So what does it mean P0 is less than P? P0, let's draw P0, P. P0 is less than P means that we are here, space-like. It's damping of space-like fields. And then again, one may get confused. I mean, what do space-like domain, does it make, when do we need it? And actually we need it quite a bit because if we then look at scattering like this, we scatter something on something. And our P, if our P is now the momentum which is exchanged here, and if this happens to be a gauge field, then this actually will be space-like. The T-channel exchange the momentum is space-like. And so then this is space-like. If we resum it, there is this Landau damping, and there's important physics there. Well, we'll come back to that still tomorrow. But so now, what have we learned? We have learned that we can do the HDL action. Then there are corrections there, and they are much more complicated than just the thermal mass. There's thermal mass, which would be d by screening. But in addition, there is a complex part, which is Landau damping. And in general, we have a complicated function. And to have that physics, to represent that physics means that our particles are not on shell, they have some spectral function. That spectral function has then a non-trivial shape. We could draw the same diagram for what is the structure of the spectral function. If there is this cut in the self-energy, then there will be a cut also. If I take 1 over that, there's also a cut here. There is a cut in the spectral function. And then in the physical domain, there can be the usual, like poles or so. Or if I were to really draw this spectral function as a function of P0 rho, then this would mean that there is something. It turns out that the spectral function is odd, but there's then non-zero weight here in the space-like domain, and then there can be the usual on-shell mode somewhere else in the time-like domain. So something like that. So there's much more structure than in just a mass. Okay, so now I want to introduce then, the exercise basically, but also the kind of what I mentioned at the beginning. And the exercise it goes under the name of the sum rule. And physically, what it means is that in the diagram which we had in the beginning, we had again this light cone, and then we had the dimensionally reduced theory here, and we had the HDL here. And so what we are now doing is that now the goal of this sum rule is to show that if you are in this domain close to the light cone, and you look at something, then even though at first sight we have to do this within the HDL theory, which is valid here, then it turns out that there is a mapping of this physics onto the dimensionally reduced physics. So that's really, theoretically speaking, very interesting. Not only theoretically, it then opens up whole new tools if one wants to do a computation, because the dimensionally reduced action is just so much simpler than the HDL. You don't have any of these logs and stuff. So if you can, sort of out of general principles, if you can show that you can map your observables here to this theory, then you can compute them in this theory, and that's much simpler. Okay, so that's why it's an interesting development. And the statement is, the claim is now the following. We have some integral, and this is basically an integral along the light cone. And why is it an integral? Well, it's an integral because, like in this sort of a situation, the exchange momentum here is not fixed. One has to, I mean, it depends on the kinematics of the, it can be, if you integrate over the kinematics of the initial states and final states, then this is P is also integrated over. So that's why it will be integrated over. And then I have my rho transverse P, and it turns out there is a P0, and that we will understand tomorrow. And then I have electric path P0. We'll also understand it tomorrow. And then, okay, let me leave here some room, and then I put here P perp squared divided by P perp squared plus P0 squared. What is P perp? P perp means that now I place myself on this light cone basically, but close to it. So this means that my form momentum has some P0 frequency, and then also the momentum is almost P0. I'm almost on the light cone, but not exactly. It has one component which I choose one component. I can choose a direction where I put the energy. I call this direction, I need more space. I call this direction some longitudinal direction. What it is precisely doesn't matter. But then there can be something else which is not the P0, which I call the perpendicular momentum. And I should have some perpendicular momentum if I'm just below the light cone. Then the absolute value of this guy has to be larger than the P0. Then I'm on the other side. So there's some perpendicular momentum here. I take it like that, and then I weight it by some combination, which also we will maybe understand tomorrow. So this kind of an integral, and so it's really an integral along this light cone, then with some weight. And so the claim is that this is very simple. It is P perp squared minus P perp squared plus ME squared. This is exactly what you would get from the transverse part in the dimensionally reduced theory, because there was no d by mass for the transverse, for the space-like gauge fields. This term is exactly what you could get from the zero component of the dimensionally reduced theory, because there it was just a mass, no momentum dependence, and there's a subtraction here, so it's the difference of these two. And so this is exactly what, this is a structure from the DR theory, and whereas the left-hand side is really HTL. Okay, so it's really a fun computation, but let me give a hint, because though fun, it's not completely easy. So hint is that this row was imaginary part and imaginary part we can write as 1/2 times I times this function minus the complex conjugate of this function. And now, however, here we are integrating over P0. And so the trick is to realize that when we do a minus here, it kind of means that we are integrating in the opposite direction. So then one can view this integral as if you were integrating again in a complex plane. You are integrating your functions, but once you are integrating above the real axis, and then you are integrating below. Complex conjugate, the complex part comes from this plus I0 plus, and when you take the complex conjugate, it puts you on the other side, and then with a minus sign, and this means that you are integrating below, but in the other direction. And the trick is to do it like this, that, okay, this is what we are doing, but now we can, since single points can be left out of the integral, we can also consider this in two parts. And then we have a contour integral along this kind of a contour of this function, and then of this function. Why did we do it like that? Because we know that there are also other appearances of P0, and here in particular there's a P0 downstairs. That's a pole. There's a pole here. And then there are P0s here, and that means there are also poles here. And so the trick we do is then that I add here a small curve, and then I add a curve going in the opposite direction. And now I close this contour here. Oops. And then I do the same downstairs. These compensate. So one's there, one's there. And then I have to show that this outer curve gives nothing. If I send it far away. And then the inner curve is now a closed contour. And so I can then use the residue theorem. I can take a pole here, and I take poles here. And then I can show that these poles give nothing. And all the contribution comes from this pole. And that will prove the sum rule. So it's sort of a nice exercise in contour integration. Okay, good. So time is out. So that's what I wanted to discuss today. And so it was a lot of stuff, but I think it's more or less I cannot. Time doesn't permit to go through all the details, but I think the main thing to keep in mind is that this HTL action, it really has a rich structure, very interesting structure, lots of physics in it, and in particular this Landau damping is an issue which one doesn't maybe appreciate, because that's really some physics that we don't have in vacuum. I mean, as long as we are just discussing thermal mass corrections, that we also have in vacuum, mass correction, masses we have in vacuum. But if we have some imaginary parts, that's not what we usually have in vacuum effective theories. And so that's the important thing, and so that will come back to then tomorrow. Good. Any questions?